So in 3D, we're going to look at something called lines and planes in space. So we're going to do lines. And I'm going to show you how to represent a line here in Calc 3. It's going to be different from the way you represented a line in your algebra class. So it may be a little eye-opening. And then after we look at lines in 3D, we're going to look at planes in 3D and how to represent those. And as we go, we will look at some sketching in 3D. Okay, we'll start with lines. So you got a line. Now, a line is something that goes off in infinity directions. Whether it's in 2 dimensions or 3 dimensions, it's gonna, and 2 points define a line. That's going to be still true in 3D. Let's talk about what you do know about lines from your algebra class, even though it's not going to be a big help here in Calc 3. When you were in 2D and you were in your algebra class, you were probably doing a lot of work with this equation. Do you remember y equals mx plus b?
Yes.
Sure you do. M was the slope, right? And b was what? Anybody remember what b was?
Y-intercept.
Good. Yep. So you all know about lines. Fine. Well, that's good news. But the bad news is in 3D, we cannot describe a line with just one equation, just like we did in 2D. Weird, huh? Well, how many equations are we going to need to just represent one line in space? That's a good question, and we'll answer that shortly. So keep your eye on the ball, and when I finish up, and count how many equations total I need to wrap into one big package just to represent one line in space. Here we go. Here's the derivation, folks. Are you excited?
Yeah.
Woo! I love it. Okay. So if you look at my little diagram here, the line L is this line right here. And I'm going to put little double arrows on it because it does go on forever, up and down or whatever it's doing. And they did put a couple of points on the line, just some arbitrary points, P and Q. And P, they gave specific coordinates, X1, Y1, and Z1. And Q is sort of more arbitrary. We can move Q wherever we want. We'll just give him arbitrary coordinates, X, Y, Z. Fine. Now, down here, there's a little vector in standard position, sprouting out of the origin, called V. And V is parallel to the line. It's parallel. So the components for the vector V are known as the direction numbers for the line, and the vector V itself is the direction vector for the line. Okay, well, how is that going to help us? Don't worry, we're getting there. So one way of describing the line, L, is to say that it consists of all infinity points. Would you agree that this line has infinity points on it? I can just keep going forever and ever. Any point, arbitrary, Q with coordinates X, Y, Z, for which the vector PQ, which we're going to form, this vector here on the line itself, PQ, is parallel to this direction vector V. So remember from our studies of parallel vectors, that means that PQ must be a scalar multiple of V. That has to be true by our picture. And so we could say PQ is equal to some scalar, I'll just call it C for the moment, times V. But I'm going to change that C, if you don't mind. I have an eraser, so I hope you're not taking notes in pen. Instead of C, since I can represent it with any letter I please, I'm going to use a different letter. So I hope you don't get mad at me. I'm going to use the letter T. And T is known as the parameter, and it's more commonly used when you're representing lines in space. Okay, so T is just a scalar, and it's also known as the parameter. We'll get to that in a moment. Now what? Well, if I actually form the PQ vector, so terminal minus initial, so X minus X1, Y minus Y1, Z minus Z1. that has to equal t times the vector v, but v was that vector down here in standard position with components a, b, c. Distribute the scalar, because you know, scalar multiplication. That's how we roll. And now we have equality of vectors. It has to be true. So we whip that out of our back pocket. We go, aha. The left-hand side vector had better be equal to the right-hand side vector. Has to be true. It says right here. So what does that promise us? It promises us that we can equate the components. So we equate the x components. We equate the y components. And we equate the z components. So what do I have here? X minus x1 has to equal at. Y minus y1 has to equal bt. Z minus z1 has to be equal to ct. And then there's one more step that most textbooks do. They solve for x, y, and z. So the x, after adding x1 to both sides, will be x1 plus at. Y will equal y1 plus bt. And solving for z, we get z is equal to z1 plus ct. These three equations taken as one big package represent this single line in space. You need all three at the same time. If you only give me 2 out of the 3, I'm going to go, I can't give you all your points. You're not describing the line completely. I need all 3 together. Nice, nice, and they all have to be good. Now, that brings us to the theorem, which is basically going to restate all this, that these 3 equations are called the parametric equations of a line in space. That's their name. So I'm going to do it officially now. A line L is parallel to the vector v with components a, b, c. That's the direction vector. And passing through the point P, get this out of the way, is represented by the parametric equations oh boy. And I'm just going to write these 3 with a big curly brace on the left-hand side. That sort of packages them into one package, looking pretty. So x is equal to x1 plus at. I already wrote these down. I'm just writing it down again, okay? At the risk of being redundant. Sorry. Y equals y1 plus bt, and z is equal to z1 plus ct. So those together, taken as a group, are the parametric equations for one line. There is another representation, and if you solve for t 3 times for each of those equations, and then set the t equal to t equal to t, you'll have this ginormous sort of double equation, if you will. And this big equation here is called the symmetric equation for the line in space. Now, I never ask you for symmetric equations on my quizzes or exams, just because I don't like the symmetric equation. So why not? So let's ask the question, why is this inferior to the parametric equations? Why do I not like it? And if you can't answer, don't worry, I'm going to answer for you. The reason why is, what if one of those direction numbers, the direction numbers are A, B, and C, what if one of them were 0? Because that can happen. Like, what if your direction vector is 2, 0, -3? Well, that means that one of these denominators is going to be 0. What do you know about division by 0? Like, what's 5 divided by 0 equal? Anybody remember from, previous math class?
Undefined.
Yeah. Thank you. Yeah. Perfect.
The world could collapse.
Yeah, the world will collapse. Yeah, and you don't like that. So the reason why is they're not valid if a denominator is equal to 0, and it might be. While the parametric equations, you never run into that problem. Heck, if one of the direction numbers is 0, yeah, so what? We're fine. We're good because we're not doing any division. So we're not in danger of dividing by 0, thank God. So that's why unhappy face next to the symmetric equations and happy face next to the parametric equations. Okay. So we're going to do a couple of examples of getting these parametric equations for a line in space. And it's not that hard yet, till we start introducing more things into the situation, into the problem. We'll keep it kind of easy. I want to summarize, though, this theorem. So what does this theorem say? Like, what are the two big pieces of info that you need in order to get your parametric equations? So, you know, you've got your line here. Ooh, I don't know what I just did. That was not cool. You got your parametric, you got your line. How do you get your parametric equations? You only need two ingredients. You need one point that lives on the line. So hopefully somebody gives that to you. And you need a direction vector for the line, a vector that's parallel to the line somehow. That's it. If you have those two ingredients, you have everything you need to bake the cake, everything you need to get your parametric equations. Okay? So this first example, example 1, notice they want both parametric and symmetric. Ah, bummer, I don't like symmetric, but we'll give it to them. They're giving us a point that lives on the line. Yay, us. That's one of the ingredients. And not only that, they're giving us a vector that's parallel to the line. Voila, they're giving us both ingredients that we need. So if you go back to the theorem, the A, B, and C, those direction numbers, the components of your vector, those are the values that you have to multiply with T. Now this T, and I didn't go over this, but it's in the theorem. This is what we call the parameter. Is it always the letter T? Most calculus textbooks use the T. There are some problems in your homework and so on. They may use an S, and will, you know, just because, hey, kicks and giggles, you can use whatever parameter that is nice. So just be on the lookout. It could happen. And then we will talk about a specific parameter later. Okay. So the A, B, and C are what you're going to multiply with your parameter. So the X1, Y1, and Z1 in this theorem are the coordinates of your point P. So you're going to go 1 plus 2t is your first equation. X equals 1 plus 2t. Your second parametric equation is y equals the coordinate of the point, -2, plus the y component off of your direction number, -4, times the parameter, t. Your last parametric equation is z equals your last coordinate, which is a 4, plus your last direction number, 3t. And there is the set of parametric equations. And we're done. Well, almost. Now they also want the symmetric equations. If you solve for t 3 times and then set them all equal to each other, that's what the symmetric equations give you. And they have this format. So for us, the symmetric will look like, I'm kind of running out of room, x minus 1 over 2 equals y plus 2 divided by -4 equals z minus 4 divided by 3. And that is it. That's the symmetric equations. I don't like them. I'm just saying. And we're done with example 1. Now, here's a weird factoid, and some students have to be careful about this because this is going to affect us throughout the rest of the semester, this key fact. And it's weird. When you get your parametric or symmetric equations, that answer may not be the only answer. It may be good, and there may be infinity other answers that are just as legit. What? Which makes it really hard for me to grade. And it makes it a little hard for MyLab Math to grade too, especially if infinity answers could be correct. So what are some things that would come into play that would change the answer but have it still be legit? Does anybody have any idea? Here's a line. You know how we used a point P that was on this line? What if somebody had a different point, like over here, but it was just as good because the line contained that point? Couldn't we use that instead? Sure. And that would give a different answer, but it would still be legit. Also, this vector V, we could use any vector as long as it's parallel to the line. So any scalar multiple of that vector would be okay to put in these factors that are multiplying with the parameter T. So there's all kinds of ways that our parametric equations would change up, but still be legit. So let's take a look at filling in the blank here. So because you could give an alternate point, have an alternate point on the line. That's one reason. So you could have an alternate point. And the second reason is any multiple of the direction vector can be used as your direction numbers, as long as it's parallel to your line. You're good. Okay, so let's take a look at example 2, parametric equations of a line. So example 2 says find a set of parametric equations for a line that passes through the point -2, 1, 0 and this other point 1, 3, 5. So let's say here's the point. I'm going to label these points. They didn't label them, but I'm going to. -2, 1, 0. How about that be my point P on the line? And here's another point Q with coordinates 1, 3, 5. Fine. Now, remember I mentioned the 2 ingredients we need to come up with parametric equations for a line are a point on the line, which we definitely have. In fact, we have more than one point. Hey, thanks guys. You gave us 2. Double the fun. But what's missing? What's the other ingredient I mentioned to get these parametric equations besides a point on the line? And this point P has coordinates.
The vector that it's parallel to?
Good. Thank you, Lupe. Exactly. They didn't give it to us. Oh man, those guys. What does that mean? Should we just put no solutions because we don't have the information? Not so quick. Take a look at my picture.
We should get PQ and like that be the same thing.
Exactly. If we form the vector PQ, we'll use that as our direction vector. It's definitely parallel to the line. In fact, it lives on top of the line. Yes. So exactly right. So let's go ahead and do that. So PQ, and I'll do terminal minus initial. So I'm going to go 1 minus a -2, comma, 3 minus 1. And folks, on your quiz, I noticed some people, they do this in their head. I want to see that intermediate step on your paper. I don't care if you're good at doing a lot of arithmetic in your head. Write it down so somebody reading your work knows what you're doing. They can follow you. Follow that logic. So then when I actually do the arithmetic, let's see what I get here. A 3, 2, 5. Great. And then these numbers are the ABC. Those are my direction numbers. So when I create this group or set of parametric equations, x equals y equals z equals, what is going to be the point that I'm going to use? Should I use P or should I use Q? Or does it matter?
I don't think it matters because they're on the same line, right?
Very good. True. So let's say you liked the point P better than the point Q for whatever reason. Fine. So your final answer would be what? -2 plus, and then you have your direction number 3t, and then you'd have 1 plus 2t, and then you'd have 0 plus 5t, and you don't have to tell me the 0 plus, so just get rid of it. Simply z equals 5t, and you're done. But what if I like the point Q better, just because, for whatever reason? So what would also be a legit answer that I should get full credit for? All right. I'm going to use the coordinates for the point Q. I still have the same direction numbers, 3, 2, and 5. So I'll have 1 plus 3t for the x, y equals 3 plus 2t, and finally z equals 5 plus 5t. That set of parametric equations is also completely legit. Well, which one's better? They're both fine. They both describe the same line in space. And this is what I was referring to when I said that the parametric equations of a line are not unique. Okay.
So I don't know. This is probably like gonna sound obvious, but like that just sort of makes equations like smaller parts of a huger sum.
Well, we're not going to get a big sum for anything here, but we're just representing
I mean,
lines.
by sum, I mean like a certain line or direction. But yeah.
Well, yeah, like this representation of the line is exactly the same as this representation. They just used a different point on the line, and there's infinity points on the line. So we can have infinity different parametric representations for this same line. We're all talking about the same guy. Interesting. Okay, let's talk about planes now. So we're going to turn our attention to planes. We're going to come back to lines on Friday. So don't forget everything. Might be good for you to review. But let's talk about planes. What is a plane? It's a surface that's infinity in directions. So I have a table right here. You can't really see it, but got my laptop on here and whatever. And it's a cheesy card table. Don't ask. It's pretty gross. But if I could imagine this flat table extending in all infinity directions, that would be a plane in space, or this wall in my office, or the floor can be considered a plane if you can imagine it going off forever. Okay. So how do you represent a plane? It turns out, good news, you only need one equation to represent a single plane in space instead of a set of equations. Thank goodness. So it's not as bad, but you got to talk about the ingredients. Let's do a little bit of review. What are the two pieces of information that you need for a line in order to come up with the parametric equations for the line? I just told you. What are they? Let's just write them down. Tell me in the chat. All right, you need a point on the line. And you need a direction vector. So those are the two ingredients you need if somebody says, hey, go get me the parametric equations for a line. You're like, oh, hold on a minute. I need to get these two things and I'll be right back. Now, it turns out, good news, you need two ingredients to come up with your equation representing a plane. Okay, are they the same? Not quite. You do need a point on the plane. And a plane, here's the flat surface say. So you need some point, I'll call it P0, some point on the plane. Any point will do. Okay? And there's infinity of them. So as long as you give me one, I'm happy. Now here's the weird part. The second ingredient that you're going to need is a normal vector to the plane. Now, the word normal in Calculus 3 is kind of a troublesome word because it has many meanings. And in this meaning, it means orthogonal, perpendicular. So let me draw the vector that I need. If I draw a vector like this, where it's orthogonal, it's making a 90-degree angle with my plane, I'm going to call him N. N for normal. If I have those two ingredients, I will be able to represent my plane in space. Okay. Let's look at another drawing of a plane. This plane is sort of tilted at an angle. It's kind of pretty though. And you can see there's a point P on the plane. And this vector N, it looks like they did draw it normal to the plane. It's making a 90-degree angle with the plane itself. So if we consider the point with coordinates x1, y1, z1, that's our point P, having a non-zero normal vector N, and let's fill in the blank. Let's give him some components. Let's say his components are A, comma, B, comma, C, as shown in the figure to the left. The plane consists of any arbitrary point Q, and they put a point here, Q, but Q can live anywhere on this plane as long as he's on there. And we'll give him some arbitrary coordinates, x, y, z, for which the vector PQ is orthogonal to that normal vector N. So what do we need to have happen? When you take the dot product of two vectors that are orthogonal, what is the answer always? We went over in a previous lecture. Anybody want to take a shot at that one?
0.
Yes. That has to be true. And then you just fill in all the blanks and make it all happen. What do I mean? They gave us the components for N. So I'm going to use component form, ABC, dot product with, now we have to form the PQ vector. You know, terminal minus initial, x minus x1, comma, terminal minus initial, y minus y1, comma, terminal minus initial, z minus z1. And you guys know how to take the dot product, right? You take the product of the x components, so A multiplied by the quantity x minus x1, plus B multiplied by the quantity y minus y1, plus C times the quantity z minus z1. That whole mass had better equal 0. And folks, this is the standard equation for a plane. So if I ask you for the standard equation of a plane on any of your quizzes or exams, please give me this one. This is known as the standard. See where it says standard equation? Now, Briggs, that would be your text, doesn't even teach standard equation. And so a lot of the homeworks, they never ask you about the standard equation. They go straight to this sort of generic thing that, anyway. One of my issues I have with this textbook. It's not my favorite textbook to teach Calc 3. There's a lot of weak points. So if you multiply out everything here, just using your algebra and rearrange everything, where the terms that have the variables x, y, z are on the left, and then you combine all the constants into one constant and you put it on the right, or sometimes they might ask you for everything on one side and 0 on the other. Either way, that's called the general equation for the plane. I like this one better. I prefer that one better. So I think what I'll do is I'm going to do one problem and then let's call it. Okay. one problem, and then we're done for the day. And we'll revisit more these equations for lines and planes next time. All right, this is a classic problem. Do you think it's going to be on this week's quiz? Mm-hmm. Yeah. It's classic. It's in every single calculus textbook known to mankind when they cover equations of planes. Just know this. You've got to know how to do it. It's not that hard, but it is involved, and I need all of your resources and brain power to do the problem. But it's fun. So we need the equation for a plane that has these 3 points on the plane. Uh-oh. What are the 2 ingredients that we need? Go back to the 2 ingredients that we need to have in order to come up with the equation for a plane. We need a point on the plane. That's one of the ingredients. Hey, good news. They gave us 3 points, not just 1. Woohoo! We win that one. We got that ingredient. But in order to bake the cake, we need a normal vector to the plane. Uh-oh. They definitely did not give us a normal vector. So let me draw a picture of what the situation is. Then I'm going to talk about our strategy, and then we'll actually do the game plan. Okay? I'm going to label these points P, Q, and R, just because it'll make it easier to talk about them. You know, they're somewhere in this plane. So here's a flat surface, here's a plane. Say there's P, you know, I'm just making this up. He say there's Q, there's R. Fine. They're contained in the plane. Fine. How am I going to get this normal vector? Here's what we're going to do. Here's the strategy. See if you can follow this, and I think you can. You're going to form the vector PQ, and then form the vector PR, and then take the cross product of PQ with PR. And when you do PQ cross PR and you use the right-hand rule, you'll get a vector pointing down and hat. That's your normal vector. Or if you prefer PR cross PQ, that will also get you a vector that's normal to the plane. It'll just be pointing in the opposite direction. I'll call it N2, just to delineate it. But it's really going to be the same as negative N, you know, because they're just going to be pointing in opposite directions, okay? Which one is better? It doesn't matter. Either get PQ cross PR or PR cross PQ, and just use that component for your plane equation. Because all you need is an orthogonal vector. I don't care if it's pointing up or down. Who cares? As long as it's orthogonal, we're happy. We can go bake the cake. Okay, so we have some work to do. So after we get this, then we can go do the standard equation for the plane, where the A, B, and C are the components that you cherry pick off of the normal vector. And then X1, Y1, Z1 are going to be the coordinates of a point contained in the plane. And we have 3 points, so you can pick whichever one you want. And it turns out plane equations are unique. So if you get an answer completely different from mine, with the exception of maybe reducing it to lowest terms, one of us is wrong. Okay. So let's take a look at forming these vectors. So PQ, using our knowledge of terminal minus initial, you know, angular brackets, 0 minus 2, comma 4 minus 1, comma 1 minus 1, terminal minus initial every time. And then do the arithmetic. Oh boy, I get negative 2, comma 3, comma 0. Okay, there's PQ, yay. PR, terminal minus initial, negative 2 minus 2, 1 minus 1, 4 minus 1. Okay, do the arithmetic. I get negative 4, 0, 3. Okay, nothing hard right now, right? I mean, what's the problem? I mean, like nothing. So what you're going to do now is a cross product. So does it matter if you do PQ cross PR or PR cross PQ? Doesn't matter, because the order is not going to matter here. Will the order ever matter? Sometimes. You know, if I said I wanted PQ cross PR, say on some quiz, do it in the order that they're asking. Here, all I need is a normal vector to the plane. I don't care where it's pointing up or down or sideways, you know, as long as it's normal to the plane. All right, so I'm going to use my, 3x3 determinant method. I hat, j hat, k hat across the top row. PQ's components in the second row, -2, 3, 0. PR's components, -4, 0, 3 in the bottom row. And then well, this is so tedious. I know, but show me all the work. Everything that I do in lecture, I expect to see on your papers, And so major diagonal, I get 3 times 3 minus the product along the minor diagonal. Wait, that's a 9, sorry. 3 times 3 is 9. 9 minus 0. Okay, then what do I have here? Oops. -2 times 3 is -6. Minus, well, 0 times anything is 0. And then here I do the major diagonal, anything times 0, 0, and minus 3 times -4, that's a -12. Got a lot of negatives flying around here, gotta be careful. I got 9i hat minus a -6j hat plus -12 is +12. Let's rewrite this in complement form just because I like it that way. So the components 9, 6, 12. There's your A, B, and C that you'll use in the equation for your plane if you check that theorem. Right here, A, B, C. And then what about the point? X1, Y1, Z1. It's up to you. You have 3 points to choose from, P, Q, or R. Just pick your favorite. I don't mind. I'll use P, the 2, 1, 1. But if you use Q or R, I just want to say that our final answer will be the same. You're guaranteed, because plane equations are unique. So you're going to have 9, this is standard form, 9 times x minus 2 plus 6 times the quantity y minus 1 plus 12 times the quantity z minus 1 equals 0. And typically they want it multiplied out and kind of make it look pretty without any parentheses, make it look pretty. Do your algebra. So I'm just going to distribute the 9, 9x minus 18, distribute the 6, 6y minus 6, plus distribute the 12, 12z minus 12. Clean this up a little bit. I want to put all the terms with x, y, z on the left and make it pretty. If I add -18 to -6 to -12, I get -36, but I'll add 36 to both sides. Now, I'm not going to give you full credit for this answer. Wait, what? I would if all 3 of these numbers didn't have a common factor. I'd say you're done. But I think 9, 6, 12, and 36 all have a common factor. What is it? What's their greatest common factor?
3.
3. Yeah, so if I divide both sides of the equation by 3 and reduce it, it'll look prettier, So that's my claim here. So if you can, and you can't always, if you can reduce your plane equation to lowest terms, and that means that all of the numbers in there, the coefficients and the constant terms share a common factor. You're not always that lucky though. So usually you can't do this, but this one you can. Final answer, 3x plus 2y plus 4z equals 12. And that is the equation of your plane. Cool, huh?